today what we want to talk about is multiplying and dividing anything with radicals and when we have binomials, because that includes adding and subtracting with radicals. And irrational numbers can have binomials as a way to write them. We learned that in quadratics. So we want to review this a little bit. This is a little bit of a review. We've done square roots. We're just throwing cube roots into the mix as well. So big idea, things that we want to remember from square roots that are also going to apply to cube roots, is that when you are multiplying, you want to make sure that we keep like things together. So when we multiply, we're always going to do the outside number, like a coefficient in front, by an outside number. I can only multiply outside numbers by other outside numbers. I can't mix and match things that are inside the radical and things that are outside the radical. We also want to make sure we just multiply inside numbers by inside numbers. So the numbers that are inside and under the radical, we're going to multiply those. And then we always want to make sure that we reduce our final answer. So this is the big idea when we're multiplying. It's actually the same rules for division. The only other rule that gets thrown in there with division is we need to remember you cannot leave a radical in a denominator. So if we are ever left with a square root or a cube root in the denominator, then we have to make sure that we rationalize the denominator. Cannot leave a radical in the denominator. This is one of the big things that we want to remember. Alright, so we can rationalize that denominator if we end up with a situation like that. So let's look at a couple of example problems that you might run into. So for example, if we have the cube root of -5 times the cube root of 25. Things that you want to remember is cube roots and negatives are okay. We talked about that yesterday. We also want to make sure that we're dealing with the same index. When we multiply, divide, add, and subtract radicals, they have to be the same index. I can only multiply a cube root times a cube root and a square root times a square root. So we do want to make sure they have the same index. Then we're going to do inside times inside and outside times outside. Good number, or good thing, there's no coefficients in front. Remember, these 3's are the index. So it's still going to turn out to be a cube root. I just need to take and multiply my inside numbers times each other. So -5 times 25 is going to be -125. And so we do in times in, out times out, and then we want to make sure that we reduce. So I ask myself, is there a perfect cube that divides -125? Well, hey, -125 is a perfect cube. The cube root of -125 is just -5. Don't forget, when you take the cube root of something and it is actually a perfect cube, then the radical goes away. So this one would actually turn out to be -5. Okay. Another example, if we have the square root of 3 times the square root of 12. Alright, so they are both square roots. We need to check and see they're the same index. There's no numbers outside, so inside times inside is going to give me the square root of 36. Again, really good news. 36 has a square root. That turns out to be 6. It does not really change anything if there's variables involved in the mix. We just have to remember from yesterday how we reduce those when there is a variable in the mix. So let's take a look at something with a variable in it so we can remember how to reduce those from yesterday. So if we have the cube root of 54x squared y cubed times the cube root of 5x cubed y to the 4th. Alright, so our rule says we got to multiply inside times inside, outside times outside, and then we're going to try and reduce it. That's the idea. Again, no coefficients in the front. Yay, don't have to worry about the outside. They are both cube roots, so we can put it together. And then I need to figure out what is 54 times 5. So 54 times 5 is 270. So first I multiplied my numbers. Don't forget how to multiply like terms. X squared times x to the 3rd. When you multiply like bases, you add the exponents. So that's going to turn out to be x to the 5th. And then when we do y cubed times y to the 4th, we end up with y to the 7th. So multiplied my in times my in. I didn't have to worry about my out times my out. So now I'm at the reduce phase. So 270, not a perfect cube. I just want to ask myself, is there a perfect cube that divides it? And the answer is yes. It's actually 27 times 10, and 27 does have a cube root. The cube root of 27 is 3. 10 does not have a cube root, so it will stay the cube root of 10. So that tells me that 3 is going to come out, and 10 is going to be left behind. So that was my first phase. Remember from yesterday, we said that when we're reducing variables, we're really interested in how many times does the index go into it. 5 divided by 3. Well, 3 will go into 5 one time with a remainder of 2. So that means 1x comes out and 2 x's remain behind. 1x comes out, 2 x's remain behind. We've got to do the same thing for the 7. So 7 divided by 3. 3 will go into 7 two times with a remainder of 1. So 2 y's come out and 1 y is left behind. So that gives me my final reduced multiplied answer, or my product there, 3xy squared on the cube root of 10x squared y for my final answer. And that's really all there is to multiplying. Dividing, there's nothing really different except for we have to remember to rationalize the denominator. That's going to be a big part of what we're doing. The only other things they can really throw at you is just remembering if I have the square root of 2/3, that's the same thing as the square root of 2 over the square root of 3. Sometimes we want to take one that's written this way and rewrite it this way, because maybe sometimes the fraction will reduce. That's always nice. Or if we have one like this, but one of them has a square root and the other one doesn't, it's easier to think of it this way, so we can take the square root of one of those numbers. So being able to write back and forth between these two is very useful. So let's look at an example of a couple of them. If I have this square root of 2/3, again, if I have it written this way, I can rewrite it this way. And this is where we have to remember, okay, well, I can't reduce 2/3. That's not going to divide any. Neither one of these have square roots. So I am going to have to rationalize my denominator. So to get rid of the square root of 3 on the bottom, well, I need this to be a perfect square. The easiest way to make something a perfect square is to multiply it times itself. So now I have the square root of 6 over the square root of 9. And what is the square root of 9? 3. And so this would actually be the final divided problem. What gets interesting is when you throw a cube root into that mix. So let's say I have the cube root of 2 over the cube root of 3. So same problem, but with a cube root this time. Again, 2/3, that doesn't reduce any. 2 doesn't divide by 3. So I need to rationalize the denominator. The problem is, I don't need it to be a perfect square. I need it to be a perfect cube. So multiplying it by itself would make it a perfect square. So that's not extremely useful unless I multiply it by itself again, because now it would be a perfect cube. If I just multiply it by itself once and not this second time, 3 times 3 is 9. 9 is not a cube. Okay, but if I multiply it by 3 again, it becomes 27. 27 is a perfect cube. So let's see, 2 times 3 is 6, times 3 is 18. So that becomes a cube root 18. 3 times 3 times 3 is 27. So the cube root of 27 is just 3, and this would remain the cube root of 18. So you do want to remember to rationalize denominators, and if it happens to be a cube, don't forget you can't just multiply it once, you're going to have to multiply it twice. If it's a fourth power, you can't just multiply it twice, I'm going to have to multiply it a third time. We want to make sure it's a perfect cube or a perfect fourth so that we can get rid of that particular unit. Now, binomials, adding and subtracting. Big ideas to remember about adding and subtracting. You can only add and subtract radicals that are exactly the same. Must be the same. Not just their index. Everything has to be the same. I can only add a square root of 3 to another square root of 3. So if I have 5 square roots of 3 plus 4 square roots of 2 minus 6 square roots of 3, the only ones I can actually put together are the two like ones. 5 square roots of 3 minus 6 square roots of 3. That'll give me -1 square roots of 3 and then the 4 square roots of 2 is just going to stay 4 square roots of 2. That's why binomials are a big part of this, because a lot of times you're not going to be able to get them together. So just remember, you can only add and subtract if they have the exact same radical, and when you do, you just add the coefficients. Add or subtract the coefficients. The square root stays the square root of 3. That didn't change. I just took 5 minus 6 to get the negative 1. So that's the big deal with adding and subtracting. And also don't forget that if you happen to have a binomial times a binomial, that you are going to have to FOIL. Let's look at an example of where you may have to FOIL. Alright, so if I have 3 plus the square root of 5 times 1 plus the square root of 5. Alright, guys, if I'm FOILing, it's a binomial times a binomial. You can FOIL or you can box. It doesn't really matter which method you want to use, but the idea is still the same. We've got to distribute. So 3 times both of these is going to give me 3 plus 3 square roots of 5. When I multiply these, I'm going to get 1 square root of 5. And let's see, outside times outside is 1, inside times inside is 25. So then I do need to look and see if I have any like terms, if I have anything that will reduce. 3 square roots of 5 and 1 square root of 5 is going to give me 4 square roots of 5. The square root of 25 is actually 5. So 3 plus 5 is going to be equal to 8. So this is what I end up with after I multiply those. You could do that with box or you could do that with FOIL.